Welcome to this lecture on Elements of Mechanical Engineering. Today, we are going to discuss thermodynamic properties. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. Currently, we are in the first module where we are studying the basics of thermodynamics. In the previous lecture, we have seen what are the different thermodynamic conditions where we have studied open system, closed system, and isolated system, and different thermodynamic functions, basics thermodynamics. And in this lecture, we are going to see thermodynamic properties. First of all, we will see what is a thermodynamic process. A system undergoes a thermodynamic process when there is some energetic change within the system that is associated with the changes in pressure. Now, if I take a system, this might be an open, closed or isolated system. When there is a energy change, then the system is said to be undergoing a thermodynamic process. For example, there will be changes in the properties like pressure, volume and internal energy. These are some of the properties which we are going to see in the coming slides. Now, with a change in these properties like pressure, volume and internal energy, etc., the system is said to be undergoing a thermodynamic process. Now, there are different types of thermodynamic processes are there which are to be studied depending on the different property change. Different thermodynamic processes are studied. Now, we have four types of thermodynamic processes. They are first one adiabatic process, second one is isochoric process, third one isobaric and fourth one isothermal process. Now, we are going to see what are these processes in detail. Now, the first one is adiabatic process. So, this is a process where there is no heat transfer into or out of the system. Suppose I have taken a closed system. In this system, we know that in a closed system, there will be energy transfer, like heat can come out or come into the system, but there is no mass transfer. Okay, so this is called a closed loop system. Now, in closed system, what happens is the energy from the outside can go into the system and the energy from inside can come out of the system. So, in this process, it is called as adiabatic process, when there is no heat transfer into the system or out of the system. So, the best example for adiabatic process is a isolated system. Isolated system. And then, second thing, isochoric process. It is a process where no change in volume occurs and the system does no work. Okay, we can see in this graph, we have a graph for here. This is pressure versus volume diagram, PV diagram. So, in this diagram, we can see the system is undergoing a process. The process is nothing but isochoric process where the pressure is constant throughout the process. Okay. Now, the volume is constant throughout the process. Now, what happens is, due to the constant volume, there will be no work done in this process. Okay. In isochoric process, there will be no work done. In the graph, we can see it is a straight line. This is a straight line where there is no work being done by the system. Okay. So, this process is called isochoric process where the volume is constant throughout the process from the beginning of the process to ending of the process. And then third process is isobaric process. It is a process in which no change in pressure occurs. So, the name directly indicates that there is no change in the pressure. So, in the third PV diagram, we can see this is a isobaric process where the pressure is constant. You can see the pressure at all the points is constant. So, this is the process from I to F, initial state to final state. The pressure is constant throughout the cycle and the area below this process is considered to be the work done by the process. Okay, so this area, this yellow color part is the work done by this process. Okay, now fourth one is isothermal process. Isothermal process is nothing but it is a process in which there is no change in temperature occurs. There will be no change in the temperature. Okay. We have fourth PV diagram here in which isothermal process is being shown. So we have a curve. This is the isothermal curve where the temperature remains constant throughout the process, but the process can be, the pressure and volumes will be varied depending on the type of process. Okay. Now these are the four graphs which indicates the adiabatic, isochoric, isobaric and isothermal processes. Now in this slide we are going to see what is a thermodynamic cycle. A thermodynamic cycle is a process or a combination of processes conducted such that the initial and final state of the system are the same. So from this definition we can clearly understand a thermodynamic cycle is a process. It is a cyclic process where the initial and final stages are same. Like if I take the example of conversion of water or conversion of ice, a solid ice cube is taken. If I have heated this ice cube, it will be converted into water. If I further heat this water will be converted into vapor or steam. Now what happens is, this is a process from where ice is converted into water and water is converted into steam. And again, if I reverse the process, like if I cool the steam, what happens? It will convert into water. And again, the water further cooling is done, the water will be converted into ice. Now this is a cyclic process where the initial and final stage of the system, of the thermodynamic system is same. Now we can see, here we have an example. In the picture we can see, this is a compressor turbine. So this is a turbine diagram where we are going to study a cyclic process. Okay. First we will study what is the working of this process. First, fresh air is taken into the compressor here. Now this compressor will send this fresh air into the combustion chamber where fuel and the fresh air will be mixed and it will be burned to produce some kind of energy. Now after the combustion has happened, the heat is taken into the turbine. Whatever the heat that is there, it will be sent into the turbine. Now what happens? This turbine will rotate using the energy from the combustion. Okay. Now what happens after that? The exhaust gases that are coming from the turbine will be taken out. Okay. Now this is a process where we are converting the chemical energy into some kind of mechanical energy. Now if you see the graph, if you see the PV diagram, pressure versus volume diagram, here we have process 1. So this is initial step where we have from point 1 to 2, we have a process line that is from 1 to 2 where entropy is constant. Here we have entropy is constant because we are not supplying any heat. In the diagram we can see between point 1 and 2 we have compressor. So we will take the fresh air from the atmosphere and we will compress the air. We are not doing anything other than that. We are not combustion. So the combustion is not being done between 1 and 2. It is done between 2 and 3. Now in the first stage, that is between point 1 and 2, the entropy is constant, which means there is no heat being supplied to the system. Now, but there is a increase in the pressure because we are compressing the air using a compressor. We are increasing the pressure. We can see in this PV diagram, the pressure is increased from point 1 to point 2. And at the same time, we can also see the volume is decreasing. So between these 2 points, this is 1 and this is 2. When we compare these 2 points, the volume has decreased and between these 2, the pressure has increased. Okay. So this is first cycle, first part of the cycle. And then second part, between point 2 and point 3, between point 2 and point 3, we are supplying some kind of heat into the fresh air along with some fuel. So between 2 and 3, we are keeping the volume constant we are keeping the pressure constant. You can see here, it has same pressure. P2 is equal to P3. We have the constant pressure, but we are adding some kind of fuel and we are making the combustion. Okay, due to the combustion, what happens is the volume of the volume will increase. The volume of the contains in the cylinder will increase. Okay. Now what happens is with the addition of energy Q in, we are increasing the volume. And then from point 3 to 4, we can clearly see that there is no heat addition or rejection. We are simply taking the hot gases from the combustion chamber into the turbine. So we can see in this diagram between 3 and 4, the turbine is present. This is 3 and this is 4. Okay. The hot gases coming from the combustion chamber will be sent into the turbine. So using these gases, the turbine will rotate and it will produce some mechanical energy. Now, between 3 and 4, we can see the pressure is decreasing. Pressure drop will be seen. Okay, between 3 and 4, we have seen the pressure will be decreasing and volume will be increasing. Okay, pressure drops and volume increases. And again, between 4 and 1, see here, in this diagram we have not drawn this as complete cycle, but between 4 and 1, we can connect these two stages by using a special device called a collector, which will collect the exhaust gases and it will send those exhaust gases back into the compressor. So between 4 and 1, we can see a process which is Q out. So we will remove the heat from the hot gas, we will cool down the gas and this gas will again be sent into the compressor. Okay. Now in this process we can see removal of the heat. And again here between 4 and 1 we can see the pressure. Pressure is constant but the volume will be decreasing. Due to the high temperature, any gases will expand. So upon cooling, the hot gases will reduce their volume. So between 4 and 1, we will get the air or gas which is suitable for compression. Now this gas is again sent into the compressor for the second step, the second process of the cycle. Okay. Now from this we can clearly understand that here this is a cyclic process where we are initially starting with air. We will take fresh air initially and this air will be sent into the compressor where it is compressed to low volume and high pressure, and from there it is sent into the combustion chamber where a fuel is added to that air and it is made to burn or combustion will happen where the volume will increase due to combustion, and this high pressure gases will be sent into the turbine where the turbine will rotate. That means it is converting the heat energy into mechanical energy, and after that the exhaust gases coming out of the turbine will be sent back into the compressor along with some fresh air so that we can repeat the cycle. So in this process we can simply understand that this is a thermodynamic process cycle where the initial stage is equal to final stage. We have initially taken fresh air. This fresh air going into the compressor and from there to the combustion chamber and from there to the turbine. Finally, it reaches out as exhaust gases where it is cooled and it is again sent into the compressor for the next cycle. So a thermodynamic cycle is also known as a cyclic operation or cyclic process. Okay. Now we'll go to the next topic, thermodynamic properties. So this is the key topic for today. So thermodynamic properties are defined as the characteristic features of a system. Suppose I take any closed system or an open system. If I take any system, it will have some properties like pressure, temperature, volume, internal energy, entropy, etc. So all these properties will depend on the state of the system. They will be changed depending on the state of the system. In fact, they will act vice versa. If the state of the system has to be changed, the temperature or pressure has to be changed. Or in reverse, if the pressure or temperature changes, the state of the system changes. Okay, they will both are directly related, and thermodynamic properties are capable of specifying the system's state. We can specify whether a system is in liquid state or solid state. We can simply identify with the help of properties. So thermodynamic properties may be extensive or intensive. There are two types of properties for thermodynamic properties. So intensive properties are the properties that do not depend on the quantity of matter. So intensive properties does not depend on the quantity of matter, which means it does not depend on the mass of the system. So they are independent of the mass. Some examples of intensive properties are pressure, temperature are some of the intensive properties. So they does not depend on the mass of the system. They are independent of the mass. And then we have extensive properties. In extensive properties, these values will directly depend on the mass. They will depend on the mass of the system. And some examples are volume, energy, enthalpy, etc. So volume is directly related to the mass. Depending on the mass, the volume will increase or decrease. Similarly, energy and enthalpy. So these properties are called as extensive properties, where these properties will directly depend on the mass of the system. So this is all about thermodynamic properties. We'll go to the next slide. So we'll study each thermodynamic property in clear. So first one is enthalpy. So we'll see what is enthalpy and how this enthalpy is very useful in day-to-day applications also. Enthalpy is the measurement of energy in a thermodynamic system. The quantity of enthalpy is equal to the heat content of a system or equivalent to the system's internal energy plus product of the volume and pressure. So this is the basic definition of enthalpy. It is the measurement of energy in a thermodynamic system. Suppose if I take a system and if we want to calculate the energy present in the system, so it is measured with the help of enthalpy. So the formula for enthalpy is, it is given in this definition. It is equivalent to the system's internal energy plus product of the volume and pressure, PV. So this is equal to enthalpy. Enthalpy is denoted with H. So enthalpy is equal to internal energy plus pressure into volume of the system. So mathematically, the enthalpy is defined denoted with H, and it is equal to the internal energy is denoted with E, where H is equal to E plus PV. Now in this diagram we can see this is enthalpy. Enthalpy is being increased. So here we can see there are two stages. Two stages are seen. So this is the stage where the system after reaction, and this is system before the reaction. Okay. Now in this picture we can simply understand that when there is an increase in the enthalpy, the system will change according to the amount of energy being supplied into the system or taken out of the system. Okay, the enthalpy will increase or decrease. Now we'll go to the next one. So this is entropy. We'll see the basic definition of entropy. Entropy is a thermodynamic quantity whose value depends on the physical state. So entropy is a thermodynamic quantity. It depends on the physical state or condition of a system. In other words, it is a thermodynamic function used to measure the randomness or disorder. So this is the basic definition for entropy, which is very ambiguous. So we'll try to understand it in simple words. So in the picture, we can see there are three types of states of matter. First one is solid, second one is liquid and gas. So when we compare all the three states of matter, in gas, the entropy is very high when compared to liquid. This is also very high when compared to solid. And in solids, the entropy is very low. So here it is very high, here it is medium, it is low. So the entropy is defined as the degree of disorderedness. When we take the matter, any state of matter, the particles are arranged randomly. If this arrangement is very random, like if the particles are not evenly distributed, then the system is said to be having more entropy. Okay, so simply we can understand from here, if we take the example of water, ice and steam. So water has three stages. Like if it is so cold, it can be converted into ice, which is solid form. If it is heated, it is converted into water, where it is in the liquid form. If it is further heated, it is converted into steam, which is in the gaseous form. So all the three stages can be attained with the help of water. So in water, when it is in the solid state, like the water is in the ice form, what happens? All the molecules, individual molecules of the ice are very keenly, very uniformly distributed in ice. The molecules are very uniformly distributed. So the degree of disorderedness, that is entropy, is very less. When we supply some heat to ice, what happens? The ice will be converted into liquid form, that is water. In the second stage, the water is in the liquid form, where it is randomly distributed when compared to solid. So the molecules are very loose when compared to solid. So here the entropy is slightly more than the solid state. And again, if further heat is supplied to liquid, what happens? The liquid form is again takes the energy. That means it will absorb the heat and the molecules will move more randomly. That it will increase the entropy of the system. So in the third stage, where we'll see steam. Now when there is steam, what happens? The particles inside the steam are very randomly arranged, and the degree of disorderedness or the entropy is very high in case of steam. So this is the basic definition of entropy. So the degree of disorderedness of any system, not only water, we can compare, or any system will have entropy. Okay. Now, for example, the entropy of a solid where the particles are not free to move is less than the entropy of a gas when the particles will fill the container. So in this three pictures, we can see the particles are fully dispersed inside the container in the third one. Because it is in the gaseous state, the particles are loosely arranged. Whereas in solid state, the particles are very tightly fixed and they are at the bottom of the container. So this is one property, entropy. Now we'll go to internal energy. So internal energy. So far we have studied enthalpy and entropy. Now we are going to see what is internal energy. So in internal energy form inherent in every system is the internal energy. Suppose I take a system. This system will have some internal energy. Initially, the energy present inside the body is called as internal energy. Okay. Now, this internal energy is what is responsible for the degree of state of the system. If the system is in solid state or liquid state or gaseous state, that completely depends on the internal energy. Different states will have different internal energies. Depending on the internal energy, we can clearly identify in which state the matter is present. So, a molecular state of motion of matter, which arises from the internal molecular state of the motion. So, that depending on that, the state of the matter will be changing. Now, the symbol for internal energy is capital U. So it is used for internal energy, and the unit for measurement of the internal energy is joules. Okay, the units for internal energy are joules. Now here we have a formula for internal energy where delta U is the change of internal energy and Q is the heat that is being supplied to the system or taken out of the system, and W is the mechanical work done by the system or done on the system. Okay. So delta U is the internal energy, which is equal to heat plus work. Heat supplied to the system and work done on the system. Okay. So this is internal energy. This is another thermodynamic property. So the next topic is work. Thermodynamic work is one of the principal processes by which a thermodynamic system can interact with its surroundings and exchange energy. So when we talk about work, there are two different manners in which, related to mechanical engineering, we will study work in two different methods. One is related to mechanical wise and second one is related to thermodynamic study. So in mechanical work, we will simply give the formula is force into displacement. So this is mechanical work. So there is no temperature involved, then the work will be calculated with the help of force multiplied by the displacement. Coming to the work in case of thermodynamics. So here it is completely different because it does not depend on the force or displacement. Here we will consider the temperature, pressure, volume, etc. Now the formula for work in thermodynamics is W is equal to minus P delta V. Here negative sign indicates work done on the system. If it is positive sign, it will be the work done by the system. Now here we'll see the definition. Thermodynamic work is one of the principal processes by which a thermodynamic system can interact with its surroundings and exchange energy. Now, in the international system of units, we have some units for work. They are measured in joules. Okay. And then another definition is there here. When we are studying the work, the rate at which the work is done can be called as power. The rate of work done is called power. Now, the units for power is joules per second. Simply, the units for work is joule. Units for work is joules divided by seconds. So, this is the unit for power. So, assuming constant pressure, what is given by this formula? So, the formula for work is W is equal to minus P into delta V. So, P is the pressure inside the system and delta V is the volume of the system, which we are studying thermodynamically. Now, so this is the basic definition of work and power. So, power is equal to work done per unit time. Then we'll go to the next slide. So, thermodynamic potentials. If we take any system while studying thermodynamically, the system will have some potential energies or some potentials. So, the thermodynamic potentials are nothing but the quantitative measures of the stored energy in a system. So, the system will have many kinds of energy inside it. There will be internal energy, enthalpy, entropy, temperature, heat. Different types of parameters are there to indicate the state of the system. So, apart from them, some internal potential forms are there where we have to describe the system using these potentials. So, the potentials will measure the energy changes in a system as they evolve from the initial state to the final state. So, these energies will make the system to change from one state to another state. Okay. Now, we'll see what are the different potentials that are available for any thermodynamic system. So, the first one is internal energy. And the formula for internal energy is U is equal to T dot Ts minus PdV. So, this entire thing is called internal energy, formula for internal energy, and this is added in extra, that is mu into dNi. Now, this is internal energy. This is one of the energy potential of the system present in the body. And second one is Helmholtz free energy. So, this is the formula given by a scientist named Helmholtz. So, that is why it is named after his. The formula for free energy equation is F is equal to U minus T into S. So, here F stands for free energy and U is equal to internal energy and T is the temperature in Kelvin and S is the entropy. Okay. So internal energy, temperature, entropy. So this equation will give the free energy present in the body. And then the third one is enthalpy. So enthalpy, we have already studied. The enthalpy is the energy of a body which is stored in the body, or which is supplied to the body or taken out of the body. So enthalpy is the amount of energy it is maybe supplied or taken out of the system. So the formula for enthalpy is equal to U plus PV. U is nothing but the internal energy, and P is the pressure, V is the volume. So this is the formula for enthalpy, which is generally we have discussed before. And the fourth one is Gibbs free energy. So now the Gibbs free energy formula is G is equal to internal energy plus pressure into volume minus temperature into entropy. So this is the formula for Gibbs free energy. If we carefully observe here, whatever the energy that is there, so in the enthalpy equation, we have H is equal to U plus PV, which is equal to H. Now in the Gibbs free energy, we can see we have this part U plus PV, which is equal to H minus TS, temperature into entropy. So this will give you the Gibbs free energy. So we are subtracting the entropy from the enthalpy. Okay, Gibbs free energy is equal to enthalpy minus entropy. So this will give you the free energy that is available in the system. So any thermodynamic system will have all these four kinds of potentials. These potentials are used to calculate or measure the change that is the system is undergoing. Okay. Different potentials are used based on the system. Depending on the particular condition, we will use each different formula. So all formulas are not used at the same time. So they will be used on the particular constraint. So that is all for today. So far we have studied the different properties like temperature, enthalpy, entropy. After entropy, we have studied internal energy, and then work. And finally, we have seen some potentials. What are the energy potentials available in a body or a system while we are studying it thermodynamically? So that is all for today. We'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.